we have flow going over top of the airfoil, we have it generally being directed downwards due to something called the cutter condition. And this results in lift for our airfoil and our airplane. At the same time, the shape of the airfoil generates high pressure underneath and low pressure on top, and this also adds greatly to our...
Another aspect of our project deals with stall. What is stall? As the plane takes off, the angle of attack is increasing. Once a critical angle of attack is achieved, stall occurs, and the plane falls out of the sky. Our system can detect stall, prevent it, and allow our plane to continue to climb. In order to understand why stall occurs in a plane, we need to understand boundary layers. So a boundary layer looks like this. You have a no-slope condition at the bottom here, which states that the flow is 0 at the surface. Moving away from the surface, we have increasing velocity until the flow velocity is equal to the boundary layer velocity. This is what a boundary looks like in the presence of a high to low pressure gradient, which we call a favorable pressure gradient. Moving over to our airfoil here, we have the high to low pressure gradient at the leading edge of the airfoil, but as that angle of attack increases and we reach the critical angle of attack where stall occurs, the flow is starting to go around the back and wrap around, causing this inflected boundary layer where the flow is reversing. In between the low to high pressure gradient, we have what we call an adverse pressure gradient. We see this inflection point in the boundary layer. As our flow goes along the airfoil, it hits this inflection point and separates off the airfoil, causing stall.
Now we can look at our overall system. So there are two parts to our system, the input or pressure sensing side and the output or actuation side. So now when our flow is going over our airfoil, we will see the adverse pressure gradient, as Graham mentioned, and our flow will start to separate over the top. Now our pressure taps on the surface are attached to pressure transducers, which are furthermore attached to our microcontroller. Once the microcontroller detects a large pressure drop across the surface, we know that stall or separation is occurring. Our microcontroller will then trigger our actuation, which is a zero net mass flux actuation. This means that on the outstroke, our actuator adds momentum to the boundary layer, helping it overcome this adverse pressure gradient. And on the instroke, it pulls down the boundary layer, so this starts to resemble a favorable pressure gradient boundary layer profile. And thus, we have detected and delayed stall.